All right, let's get right into it. We're going to talk about deploying new tech into what's called operational technology, or OT environments. And look, this is not your typical software update, not even close. This is a world where every single action has to be thought through, super carefully, because the consequences, they can be very, very real.
And this quote, yeah, it just nails it, gets right to the heart of the matter. We're not talking about a best practice here. This is pretty much a survival principle. When you make a change in an OT system, I'm talking about things like manufacturing plants, power grids, automated labs, it is a huge, high-stakes event. It's something that directly affects the physical world.
So what's the big deal? Well, you've got to understand the difference in the stakes. In the IT world, right, if a deployment goes bad, maybe a website goes down, it's frustrating for sure, but you can usually roll it back. But in the OT world, oh man, a failure can mean millions in damaged equipment. It can bring a whole production line to a grinding halt. Or, and this is the really scary part, it can cause actual physical harm to people. The risk is just on a completely different level.
And that really gets to the core of why OT deployment is such a different beast. See, these aren't just systems shuffling bits and bytes around on a server. Nope, these are systems that control physical reality. They're the ones moving giant robotic arms, opening and closing massive valves, mixing precise chemical compounds. So a software error, it's not just a bug anymore, it's a potential physical incident.
Okay, I know this diagram looks a little complicated at first glance, but it does a fantastic job of laying out the whole landscape. Let's just focus on the two main parts. Down at the bottom, you've got what's called the execution plane. This is where your IT systems on the left are talking to the physical OT systems on the right. But the real magic, and frankly all the safety, happens up top, in the control plane. You can think of this as the brain of the operation, or maybe like an air traffic controller. It's the layer of governance making sure every digital action is checked and double-checked before it's allowed to touch any physical machinery.
So how in the world do you manage all that risk? Well, that brings us to our very first critical safeguard. You have to establish crystal clear deployment boundaries. This is all about defining, with zero ambiguity, exactly what a new system, especially something like an AI, is allowed to do and where it's allowed to do it. These boundaries can't be fuzzy. They have to be totally explicit.
And you should think about these boundaries as a kind of spectrum, or maybe a ladder of authority. You always start at the safest possible point. Step 1, read-only monitoring. The system just watches and learns. That's it. From there, maybe you move up to Step 2, advisory recommendations. Now it can suggest actions for a human to take. Then you get to the next big leap, Step 3, gated execution. This is where the system can finally act, but, and this is a huge but, only with explicit human approval. And then way up at the top, the highest level of risk and authority is fully automated control. And honestly, that's a boundary most systems should probably never cross without some seriously extreme, proven in advance safeguards.
Let's actually see this in action. If we go back to our main diagram, look closely at these approval gates that are highlighted here in the control plane. That right there is the boundary we were just talking about. An action that gets proposed by the IT systems on the left can't just hop over to the OT side on the right. No way. It has to pass through these gates, and these gates are a non-negotiable checkpoint where a human, a person in the loop, has to sign off on the change before it can have any kind of physical effect.
Okay, let's move on to our second huge safeguard. And this one kind of flips the usual way of thinking on its head. So many people treat rollback as an afterthought. What do we do if it breaks? In OT, that's a recipe for disaster. Here, rollback has to be a primary design requirement. You have to design the fire escape before you even draw up the blueprints for the building.
Because let's be real, no matter how much you plan, something is going to go wrong. It's just inevitable. A sensor will fail, a model will see some weird data and misinterpret it. Something. So the question is, what is your plan for when things go sideways? And if you don't have a predefined, rehearsed answer to that question, you frankly already failed.
And our diagram shows us exactly what a good answer looks like. See these bright red pathways, the ones labeled emergency rollback and stop/revert? These are not improvised escape routes you figure out in a panic. No, these are engineered, tested, and clearly marked paths to safety. They give you a way to immediately halt execution, revert a change, or get a human operator involved, like right now.
And you have to understand, an OT rollback is so much more complicated than just reverting some code in Git. We're talking about actions that could involve physically switching a machine back to manual operator control, or safely shutting down an entire production line in a very specific sequence to avoid damage, or just immediately getting an operator on the horn to intervene. These are complex, physical actions, and every single one has to be planned for.
And this gets to a really common and dangerous misunderstanding, especially for folks who come from a pure IT background. You simply cannot assume that you can improvise a rollback on the fly. It just doesn't work that way. In a regulated, physical environment, making that assumption doesn't just cause downtime, it causes incidents. Your rollback plan has to be every bit as robust as your deployment plan, period.
All right, our third and final safeguard really ties all of this together. It's a simple but incredibly powerful idea. The more authority you give a system, the more rigorous its safety and rollback mechanisms have to be. To put it simply, risk scales directly with autonomy.
Let's break that down a bit. A low-authority system, one that's just giving advice, you can probably get by with a human operator just ignoring bad advice or correcting it manually. No big deal. But a high-authority system, one that's directly controlling heavy machinery, that thing absolutely requires explicit, automated, and pre-tested ways to stop itself and revert its own actions. The rigor has to match the risk. It's that simple.
So when you put this all together, what's the big takeaway? Well, it creates a really clear mandate for anyone, and I mean anyone, designing systems that are going to touch the physical world. Safe design isn't just another feature you add to the list. It's the entire foundation. It means you are building in staged rollouts, explicit human approval gates, and, most importantly, predefined rollback actions from the very first day of the project.
And just so we're all on the same page, let me be crystal clear about what this explainer is and what it isn't. What we're doing here is explaining the core principles for safe design. We're trying to prepare teams to think about these complex challenges. What we are not doing is prescribing a specific automation strategy. And we are absolutely 100% not approving or authorizing any specific deployment. That responsibility always lies with the teams on the ground.
Ultimately, it all boils down to this one idea. Working with OT systems demands a fundamental shift in your mindset. It's all about having a deep respect for the unyielding laws of physical reality. And in that world, having clear boundaries and pre-tested rollback plans, well, that's not just good engineering. It's the essential, non-negotiable mechanism that protects people's safety, protects expensive equipment, and protects the entire operation.